live.
Hello, everyone, and welcome to another episode of Solving Advent of Code in Rust and trying to learn Rust in between. I'm Eugene. We've got Roberto and Luciano here with us today.
Hello.
Hello.
Thanks, everyone, for following along. If you never did Advent of Code, this is a coding challenge which is published every year in December, in the days leading up to Christmas. You can find it on adventofcode.com, and I'm going to try to put a banner for that, unless Luciano's already done so.
I was not ready at all, but I can try.
Click to show this message. There you go. We should be getting it now.
Nice. Good job.
Right, you can find them on adventofcode.com. We are publishing all of our code on GitHub, and I'm going to put a banner on for that. We're publishing everything on github.com. You can check it out there. Pull requests are very much encouraged and appreciated. There's also a link for this in the description of the Twitch channel. So this episode, we're going to be doing exercise 15 of last year's Advent of Code. So perhaps we'll go through the README first. I can do that, and then we'll go through the Python and Rust version.
Meanwhile, I want to say hello to Typed the Reflections. I hope I'm reading it right. First time chatter here. So thank you for joining us, and feel free to send us suggestion, comments, critics, anything is well accepted.
Offenses.
Also, maybe less well accepted, but who knows?
Fair enough. All right. Are we sharing my screen so we can go through the README?
Yes, let's
Perfect.
go through it. And also, Gramsco, thanks for the follow.
Nice. Very active today. Thank you all for this. So today's exercise is probably, as the title of the stream suggested, going to deal with finding paths. Essentially, the story that we get is that we're riding our submarine still. We're in a cavern, in a cave system, and there's danger because of chitons. I'm not sure exactly how you pronounce them. They're like some sort of mollusks. Anyway, the goal is not to bump any
You
of
can
them.
click if you're really curious, if you want to show.
I did, but I'll show it to everybody else. So they look like this. They're like kind of weird and colorful. Anyway, so the cave is full of these guys, and our goal is to not bump into any of them. Our submarine maps out the risk for the path that we're going to go on. The risk is basically how many of those mollusks are on the wall, and the goal is to find the path with the smallest risk, essentially. The risk is a number between 1 and 9, as you can see it in the example here. We start in the top left position, and the goal is to get to the bottom right position. And I think the first question was to be able to calculate the risk of a path from top left to bottom right, which I think the question here isn't the most clear, but I'm assuming it's a diagonal, top left to bottom right, or something in the lines of that. I'll go through part 2 as well, maybe, and then we can just show the code directly, because they're usually pretty linked together.
Yes, yeah.
So for part 2, the cave is actually 5 times larger, which is always a bonus. It means that we can't just brute force our way around, and we originally scanned just a small tile of it. Also, all of the risk levels are actually 1 higher than the ones that we had before, and the maximum risk level stays at 9. If any of them has to go over 9, it'll just reset back to 1. So they're giving us some examples here. I don't know if they're necessarily the most helpful examples, but essentially anything that was a 9 will be moved on to right. Each single digit corresponds to... Sorry. I shouldn't be reading it because this is all that matters, essentially. Equipped with a full map, we can now find the path from the top left corner to the bottom right corner with the lowest total risk. And that's actually the question that we had. What's the lowest total risk?
So if I remember this correctly, this grid is something we could imagine as a graph, right? Where every cell is like connected to the other on the top, left, right, and bottom, right? And then there is a cost in moving from one cell to the other, which is the cost of the current cell, right?
Yes, if I remember correctly, it is.
That basically adds to the risk, yeah. It's our risk accumulator, if that makes sense.
Okay, so it's like basically a weighted graph, and we'll need to traverse the weighted graph.
Exactly.
In some way.
each node of the graph has a maximum of 4 connections and a minimum of 2, basically.
Okay.
So yeah, this is it for the README, I guess. Who wants to go first? Do we want to go through Python first, or do we want to go through Rust first?
We can show Python. I solved it in Python, probably not with a graph algorithm, so we can show what I did. Then we will compare with the Rust solution.
Cool.
So here is the parsing. So this is Luciano input. I already updated mine with this. This is just map to integer all the character as a list, because map in Python 3 is a generator. So I want something material. So give me a list of all the x mapped, that all the x are the character, mapped as an int for all this guy, that is a multi-line string, splitted by line, because every line is a row, and from the row I go to a cell. The usual list of lists representation. Part 1. Part 1, I'm starting getting the size of the input matrix. I create another matrix of the same size, empty, with known values on them. I start from the top left, 0, 0, with a weight risk of 0. I put in my list of stuff to do. Now here I have a stack. I could have done just a counter. I realized that it later. I will show a graph to explain this better. But basically I start from 0, 0. I take the number from 0, 0. I do some kind of edge check just to be sure that I'm not going left when I am on the first cell, or up when I'm on the top cell. The new value is my current value plus the input grid. This is to go x minus y, so this is to go left. Obviously, in the first cell, we will not go left because we are already there.
Mm-hmm.
So we will go here. So we add the risk of the new cell will be the current risk that we are on plus the risk to move to the cell to our right. If the cell to our right is known, remember that I started with an empty matrix, or if the current value of that cell is already computed and it has an higher risk, I updated the value to go to that cell with the new value that has the lowest risk. At this point, I know that I have to go in that cell and try to see what is the danger going on in that direction. So I append it to my stack. And I do this for the 4 directions, if we can go in that direction. At the end of all this loop,
can I make a small comment that maybe it's not too obvious? Keep in mind that all these if statements are not like if else. So you could literally enter in all the 4 of them in one round. So that you could accumulate up to 4 new directions basically every time we are visiting a cell, right?
Yeah. Then the last value in the bottom right corner of our matrix of values is the solution. To show this graphically, we can show this graph that is on the, I think this is the README input, is a smaller grid. I parse it. This step function is a generator that is giving me the new value of the matrix that here doesn't start with known in it. It starts with -1. Why with -1 and not with known? Because -1 is a not valid risk, because the risk starts from 0 and goes always on the positive numbers. -1 is a trick to say known, because I'm plotting that with matplotlib, and doing a matrix show is not taking in knowns because it can't know how to plot them, and so it's throwing an exception. Instead, here I'm using matplotlib, so my starting, I think I can make it a little bit, okay, so it fit. So my starting state is this one. Every time I have a step, you see, the first cell has a risk 1. So to go right or bottom, the risk of those 2 cells are 1. Next step, this cell has probably here 6, because to go right, you have 6. To go down, you have a 4. But you probably had a 8. But going from this one to here, it was probably a 3 here, so 4 is less than 8, and so I keep the 4. Then we go on like this. See that here there was a 15 computed. Then when we moved, this become a 12, because going from this cell to this cell is less risky than from this cell to this cell. So it's computing the new risk, overwriting the old one only if it's lower. This 5 become a 4, and so on.
So basically, for every cell, you know the previous value that you're coming from. You know the current value to go to the next cell. And then if that cell doesn't have any value yet, you assign the current cost to get there. If there is already a cost, you need to evaluate, is that cost
if it's cheaper,
better or worse? If it's cheaper, you replace it. If it's higher, you
go in
it.
that, and I go in that direction. Because this is also taking account propagation to the left. I don't think in this input there is any of them, but I'm also taking in account that you can do some S to go through the matrix if the weights are in a certain way. I don't think there is anything like that in this input, so I'm taking too many stuff in account. But again, I was not knowing when I started. So after we do all our computation, we arrive at the bottom right, 44, 46. The 44 become a 39 because it's lower, and the last one is 40. And this is the solution to the README example, starting from there and going there.
Nice.
It's possible to do the same for the part one. Oh, this is what is this? Is another README example. Is a little bit bigger, this one, so it's not the README again. Let me zoom out so you can see all of it. This one again is doing the same, but with more cells and more numbers. So we go through, obviously, now you can't read the numbers. It's interesting to see the last step, that is our path. Starting from the last cell and going backward to the lowest numbers, we are creating the path that the submarine has taken to go from top left to bottom right. There is also here the one with the
the comment almost biological. Yeah, so it looks kind of
this
cool.
Is a 500 by 500, so now the numbers are not plotted, those are just the colors that they gradually fill in, and the last step is our path to go back to, and this is this was my input, not Luciano's one, but in the end yeah, you see here they also go up in a certain point. Here you can see that they don't just go right and bottom. In this place they also go up because there was a better way of doing that. I think it's the only place that has this strange behavior of going up, but yes. So let's look at the code now that I explain. Okay, part one, we already looked at the code, to be honest. This was just to explain a little bit better what was going on. The code is all of this. And like I said, probably now it could have been done without a stack, thinking about it again. The answer of part one is 687. I think the README agrees with me.
There's also a question from Type Reflections. They're asking if there's a kind of a greedy solution where we make the least risky move at each step instead of exploring.
That could not work because probably could, or because there are situations, probably not in this example, while you can take this direction, because at the beginning, for example, if there was a 2 here and a 1 here, you go right because 1 is less than 2, but then the 2 leads you to 1s and the 1 leads you to 7s, and so from there is more expensive. So,
but I think if we implement Dijkstra, which I think is what I did in the Rust solution, it is grid in that sense. So it tries to pick always the minimum path to a certain node locally, with the idea that eventually that will lead to the optimal solution globally. And it doesn't mean that it can be wrong. It just means that more often than not, it does find the cheapest path faster. Sometimes it doesn't, just because the graph has weights that are not always promoting the local minimum. So sometimes it will recognize just a little bit later that there was a better path and update the view at that point.
Yeah, probably there was a greedier solution to this. This is a little bit brute force, I admit it. But was running. So when you do advent of code, there is always this approach of having the solution fast to beat the other in your local leaderboard. And so you come to quick and dirty solutions.
Yeah. Right. Sorry for the small derailment. Go ahead, Roberto. You were going to go through part two, I think.
I'm done. Do you want me to show part two too?
I think
right
so,
now?
yeah. Let's
Okay, let's go to part 2. That is the...
So let's recap what was the difference between part 1 and part 2. In part 1, we just wanted to find the minimum cost from top left to bottom right? What is the difference in part 2?
Part 2 is 5 times larger because it's replicating the 5 grids on the side of each other on width and height. So it's 5 times larger, and is replicating the values, adding 1 when you go to the right and 1 again when you go to the bottom. And if the value go above 9, it roll back to 1.
And the ask is to find the shortest path.
And the ask is always the same.
Sorry, not the shortest, the least risky.
Least risky, yeah. But we can call shorter, but
well, yeah.
For a graph is the shorter one.
Yeah.
The main code is exactly the same. I start with this huge matrix. I start top left. Sorry, left. Yes. I go in all the directions, so the code is exactly the same. The only difference is here to get to access the weight matrix. I'm not addressing the matrix directly. You see here I was adding the grid directly. Here I created a function called get that is getting from the grid. And what the get is doing is not really creating the multiplied version of the grid in memory, but it's just accessing, because you are replicating. If you do modulo by the size, you get the same cell. So you can compute which cell do you want. Then, based on which replicated tiles you are on, you have to increment the cell value, this red that we have here. If we go above 9, we roll back to 1. And if we go to the right or if we go to the bottom, so the new weight of the new danger, the new weight to move from this cell is this red. So I just changed this piece, so those two solutions can go in one with just providing a function to get the data out for the risk, providing two different functions to the two different call of the same function. I could do this refactor one day. And then the answer is always the bottom right cell, that is, in our case, in the README case of Luciano, 2957, that I think is matching with the README.
Yeah, 2900.
So the algorithm is not changing, it's just changing how I access the danger list, the danger grid, or how do we call it?
The danger zone.
The danger zone, yeah.
Highway to the danger zone, even. Sorry.
I am the danger, just to quote Breaking Bad.
Nice. Was that portion of the show finished?
Let's go to Rust at this point. Let's see how Luciano implemented all of this.
I'm going to try something that I'm not sure I'm going to be capable of, but let's give it a shot. I want to try to explain the Dijkstra algorithm first, because that's what I used in my own implementation. So basically, if you haven't studied the Dijkstra algorithm in computer science, it's something that is very common to look at during university. But if you haven't done it, it's one, I suppose, famous algorithm that can be used here, because it's an algorithm that allows you to figure out in a weighted graph what is the shortest or cheapest path from one point to another of the graph. So here, what we will do is basically use that algorithm to determine the cheapest path from the top left corner to the bottom right corner. And at that point, we have the solution. And I have a feeling that what Roberto implemented is some light variation of that algorithm. So that it could be interesting also to see if we spot some interesting difference between the two implementations. So I'm going to try to sketch it very quickly, but I don't have any examples. So let's see how it goes. But basically, the interesting thing is that our grid can be represented as a graph. So just as an example, let's say that we have a grid 3 by 3. So we have, 1, 2, 5, 4, 1 again, 2, 3, 2, and 1, right? If we were to represent this as a graph, it's basically you have one node that to go here costs 2, to go here it costs 5, and then we have another node here that costs 4, another node here that costs 1, here it costs 2, here it costs 1 again, here it costs 5. Does this make sense, or am I doing it wrong?
No.
Okay, then here it costs 4.
I mean it makes sense. Apologies.
And then from here to here costs 1, 2, and this one is 2 as well, I think. Hopefully that's correct and readable at the same time, but it's just an example. So if I get some number wrong, it's not going to necessarily affect our solution. So the thing is that we'll need to give labels to all this node just for simplicity. So I'm going to use and color, and we can call this one A, B, C, D, E, F, G, H, I. Actually, we can zoom a little bit more. Hopefully it's more readable.
I was going to say it's not super readable right now, so maybe... Yeah, perfect.
So what Dijkstra does is basically allows you to figure out, in our case, we want to find, let's say, the best path from this point to this other point, right? We can take any route, but of course, every step we take has a cost. So we'll need to figure out how to get from A to I in the cheapest amount of moves. So the way that the algorithm works is in 2 phases. There is one phase that is like decide which node should be visited next and update the local state. And then you basically move to that node and repeat the previous step. And every time you do a step, you have a better partial view on the cost of moving across all the nodes, not just, well, you set the starting node, so that's always A in our case, but you basically are computing the cost of moving from A to any other node. And of course, we will get also the cost to move from A to I. So maybe this is a slightly different with what Roberto did. Here we are kind of exploring a little bit more of the space. And while we do that, we basically need to, our state is going to be a node. So for instance, we always have A. Then we have the current cost. So let's say cost and the previous node. Previous, I cannot write to. And the starting point is that from A to go to itself, what is the cost? 0, of course, because like we are already in A. And then from A to go to any other node, what is the current cost? We don't know because we still have to figure it out. So our best bet is to say that that cost is extremely high. So for sure, as soon as we start to discover paths, we are going to update that value. So we will say theoretically that the cost to every other node is infinite. So I'm going to say B, C, D. Now, I'm not going to do all of this because it's going to take forever, but I just want to do a few steps just to give you the idea, and then we're going to look at the code. So we say that initially the cost is infinite, infinite, infinite. So the first step, we start from A, and we need to select the next node and update the state. So from A, we can go to B and to D, and we see that to go from A to B, it costs 2. And to go from A to D, it costs 4. So this is already something that we can update because we can see, okay, to go from A to B, I am, very big eraser. I am seeing that the cost is 2, so I can already update that. And in the case of D, I am seeing that the cost is 4, so I can already update that. And another thing that I want to keep is a set with all the nodes that I have already visited, because I'm not going to visit a second time a node that I have already visited. So in theory, we also have visited, and visited contains A, B, C, D, E, F, G, H, I. So A, we can consider is already visited, so we remove it. The next one we want to select from A is B, because B is the cheapest option we have right now. So it kind of makes sense to follow the cheapest option. So what we do is the current node now is not this one anymore, if we can delete, but it's going to be this one. And now we have to repeat the same algorithm. So we are from B, and we see that from B we have a bunch of different choices. We can go to C, we can go to E, we can go back to A, but A is already visited, so it doesn't make sense to go back. So the only two really options we have is E and C. So I'm going to add E here just because it's convenient for our example. And right now, let's assume it's infinite. What we can see is that to go to E, we have a cost of 2, but this is just a local cost. We have to remember that to get to B, we already spent 2. So in reality, the cost to go from A to E is 4. So here we can write 4. Then to go to C, the local cost is 5, but again, we are starting from a cost of 2, so the cost is going to be 7 to go to C. So we can say here that the cost is 7. So at this point, we visited B, and we have to select the next one between E and C, and we select E because it's going to be the cheapest option we have so far. And this basically will keep going until we reach our destination node, in our case, I. And at that point, we know exactly what's the cost of I. One thing I forgot to do is to mention the previous node. For instance, here I should have said that the previous node is A. For D, the previous node is A. And then for E, we said that the previous node is B. And actually, we only update the previous node when we visit. So we haven't visited D yet. So this one doesn't even have a previous node. And then at the end, when we find our path, our cheapest path, you can start to look similarly to what Roberto showed to all the previous node, and in reverse you are going to construct the entire path from the destination to the beginning, and that's our cheapest path. Does that make any sense? Or
it sounds pretty much exactly like Roberto's solution.
Yeah, I don't know if there is any obvious difference, to be honest. I wanted to go through it because I'm sure that there is a small difference, but
the difference is Roberto's deals with a two-dimensional grid, which means it goes left.
Yeah,
right,
I don't give
bottom,
names.
top.
I don't give name to the nodes.
Yeah,
I just keep at this matrix of the costs.
exactly.
But as a matrix, so I want to get the cost of the node 5, 4. I go in that matrix at the coordinates 5, 4, and I have the cost for that to go to that node.
Yeah, that's
and I don't keep a list of visited nodes because I go to a node, I go back to a node that I already visited only if I find a better, cheapest way to go there.
Also,
so if I already visited a node, but I had 7 to go there, and going from another cell that is around it, I can go there with 6. I replace that weight with 6, and I add to my stack. Go again in this cell and try to go on from this cell again to see if we can find a better.
And I think that maybe that's the difference, because I don't think in Dijkstra algorithms you revisit the same path, the same node. You only update the view. So you will say, okay, I realize that to get from A to this other node, now there is a shortest path. Then I don't care to resume the visiting from that node because somehow I'm still exploring all the nodes.
Also, another notable difference is the Dijkstra algorithm can take any number of connections to other nodes.
Yeah.
Because it is a graph, so you could have a node that's connected to 2, and then another node is connected to 7 other nodes, and it will try all of them. It's a bit more abstract, if that makes sense.
Yeah, here is just a very specific graph that looks like a grid more than a graph, and we have to imagine it as a graph to use the Dijkstra algorithm.
Yeah, I stuck with the grid representation of data.
By the way,
because it was easier to plot them as a matrix. Plotting a graph is always a pain.
I was gonna say, if anybody in the chat knows how to pronounce this algorithm's name, it would be nice, because all of us say it differently, and I'm sure neither is correct.
Oh yeah, I challenge you also to try to explain in a chat how to pronounce Dijkstra or Dijkstra or whatever you want to call it.
Digestra.
Anyways, okay, let's start to look at the code. So what I did, ignore all the imports, but basically I started by defining struct that represents the edge of the graph. And I'm not really giving it a name like A, B, C, and D, but I'm keeping in mind the position in respect to the original grid. So this is kind of my label for every single edge, is the X and Y position from the source grid. Oh, somebody has an answer for this. I still wouldn't know how to read it. Thank you. Thank you, Gramsco, for suggesting this, but I'm going to keep saying it Dijkstra. I don't know if it's the correct way of reading it.
My chat disconnected. I didn't get to see it. Ah, I see it now on the screen.
Yeah, it's a phonetical notation, but I don't remember how to read it. So.
I think. Or maybe I don't know.
Dijkstra? No idea.
Going to go to Google Translate and try
it. Yeah, you can pronounce it from Google. Anyway, so meanwhile, I'm going to keep explaining this one. So position is our unique identifier for a node, basically. And then cost is the value of that cell in the grid, which represents the cost from moving from that node to one of the adjacent nodes. Then I have this idea of I need to make the different edges comparable. So I implemented the ORD trait, which basically allows you to say, okay, if I have two structs of the same time, of the same type, can I say this one is bigger than the other? If you implement this trait, you're basically telling Rust how to do that comparison. And you have total ordering and partial ordering. I don't remember what's the difference, but I think in partial ordering, you can return an option. So it can be known if you don't know which one is bigger. So I'm not really sure, but I think I needed to implement them both for being able to compare the instances of the same type.
I've spent the last 20 seconds in a very important manner. I found out how to pronounce it, Dijkstra, because the guy was Dutch, and that's how you say it in Dutch. So there you go. Problem solved.
Okay. Nice.
Important, very important.
I don't know if I'm going to remember, but good to know.
Sorry.
Okay, then other than that, we have a cave map, which is literally our grid. And this is using cost generics, because this way we can make it as big as we want, and it's statically going to allocate an array that is as big as we are saying with this n parameter. And the cave is literally a grid of U8 sides n by n. So then what did we do? We implemented a from string that allows us to convert our input text into a cave map. Remember that the input looks a little bit like this. So Roberto already showed it, but it's literally like 1 digit per cell. And it's probably 100 by 100 or something like that. So what we are doing here, we are taking this text and converting it to this structure here. And I'm not gonna bore you to death with the implementation here, but it's basically reading one character by one character and filling in the values in this bidimensional array. Then we also implement a display here just for debugging. You can visualize the grid in a little bit better way, but I don't think we even used this one. Maybe I was using it for development. And then finally, we have this cave map, and there is this expand map, which is the one that a function that we use for part 2 to basically take the original data and expand it 5 times. Now here, I think I'm doing that literally. Like I'm actually allocating 5 times more memory or not. I think what Roberto did was way smarter.
I think you're doing because you are using the n as a constant to allocate a bigger type. So somewhere probably you are doing that allocation with the turbo fish to give the but you are taking n as a constant somewhere and doing the math.
We need a turbo fish emoji.
What am I doing? Let's see.
N use size. What are you doing with n? You are using that n somewhere in the expand map code.
Oh, I think I am assuming that you already gave me the size 5 times bigger.
Okay.
I am ashamed of myself. We should improve this one. Definitely we should do something smarter where we have a function that just gives you the data and can dynamically compute the data because it's going to be a repeating pattern as Roberto showed. So it doesn't make sense to physically repeat that pattern 5 by 5, so like 25 times, right? When you can just keep it once and have a virtual view on that one grid.
I went for the virtual view because of memory or because I was lazy. One of the two.
Yeah, but it doesn't make sense to do Rust and pretend we're writing very efficient code and then you do crap like this. So I apologize for this mess and maybe we'll get the time to fix it.
Yeah, keep Python for doing crap.
Yeah, it's called prototyping. So, okay, let's look at the interesting bit. So this is actually the implementation of Dijkstra. How did you say it?
Dijkstra.
Yeah. Dijkstra, okay. I feel very fancy.
Very Dutch now.
Okay, so let's start with this. So this is basically this is a function on the struct itself. So you have a cave map and you can run this algorithm and it's going to give you a U sides where that's the cheapest cost from going from the top left corner to the bottom right corner. So it's a very specific implementation of the algorithm. So it's readjusted a little bit to the specific problem. So we start with creating a distance hash map, which maps the position from, so this is kind of a label for a cell or a node in our graph, if you want. And U sides, I think, is the current cheapest cost that we have seen from A, so 0, 0 to that particular cell. Then we have active nodes, which is a binary heap edge. Now, this could be interesting. This is an optimization. But basically, because we want to always pick the cheapest path, by using a binary heap, you can easily keep the connection between the nodes and make it very fast to get the minimum node from the current node to the next one. I don't think this would make a huge difference, to be honest, but I mean, you already have it implemented in Rust, so why not using it? We could measure maybe the difference with another implementation. And then the first thing that we do is we are starting from 0, 0. So we are already in 0, 0. We know the cost is 0. So we insert that value. Everything that is not in this distance hash map, and that's the reason why I'm using an hash map, I can consider that's infinity cost to get there, just because we don't know yet what's the cost to get there. So we can assume maybe there isn't even a path, so it's infinity. Mm-hmm. Then initial path is gonna be the current edge that we are starting from. So the current cost is 0 and the position is 0. Active nodes, we just push the current edge there. Now, the other thing that we do is we need to repeat this thing until there are nodes that we need to visit. So here, what we're doing with this while let some active nodes pop is basically a fancy way to say, try to get one element from the active nodes. This element is going to be an edge, but also destructure the position and cost. So inside this loop, if there is at least one node, inside this loop, we can easily access the position and the cost of the current node. So this is a little bit of a syntactic sugar where we're doing checking if there is a node. If we get that node, we also destructure the position and the cost, and the loop will do one iteration at that. Stop me if I say something stupid or non-clear.
But well, these active nodes is like my stack in Python. Is where you put the...
Pretty much, yeah.
Yeah, you put the initial position and all the position that you have to go on with, and then you pop from it when you at every cycle.
Yeah, and to be honest, I don't think I'm keeping a list of visited nodes. So I think I'm using an approach similar to yours, where it's like, yeah, if I find something again in the stack, probably I'm gonna visit it again.
Also, because you can have a strange configuration then. That you visited a node, but doing another trip, you can get there with a cheaper solution, even if you already visited one.
Yeah, I'm not entirely sure about that, but I mean, you're probably right. I'm just struggling to figure out an example. Anyway, we can figure that out later. Yeah, syntactic sugar, absolutely. So here what I'm doing is... what am I doing here? If position is n-1, n-1, so this is the destination. So that means we found our destination node. At that point, we just return the current cost. So it's like we have been walking around randomly. Suddenly, we found the shortest path to the actual node we were looking for. So that's our solution. So this is what's really going to happen last. Then let's see what happens in another more generic case. So we need to check if we already found a better path. So we take from the distance, which is basically our state, we take the current position. If there is no current position, we insert usides max. So we are saying, okay, it's the first time we are seeing this thing. So that we can assume it is as big as it gets of cost to get there. Then we compare the current cost with this value, which can be either a value we saw before or the maximum, so or infinite, so to speak. And if this cost is bigger, we continue, which means ignore this path because it's going to cost me more to go there than what I have already seen before. Otherwise, if we get here, you can basically say, okay, this new path that I'm finding is actually convenient because it's cheaper than something I've seen before, or it's the first time I am exploring this path. So what we do is we need to get all the neighbors of this position. And actually, where did I implement the neighbors? Oh yeah, it's implemented here. So I have a utility function that will give you the connected ones. And this one looks incredibly similar to what Roberto did, literally. Like multiple if statements, checking boundaries, and then pushing the neighbors in a final result. So we get all the neighbors, and then we say, for every neighbor, create an edge, initialize this edge, and then what do we do with next? We check to update the state. So we figure out the distance from the current edge to all the neighbors. And notice that here the cost is going to be the current cost for the current node plus the cost of that neighbor. And finally, we say if the cost to go there is lower than the current cost I've seen so far to get to that particular edge, then I'm going to push the current node to the active node. So I'm going to consider that this node is something that I want to explore. If not, it's just going to ignore that node and keep going. Now, this is unreachable because in theory, this loop is repeating itself until it finds this condition and we return. So just to recap, what's going to happen is here we found other nodes potentially to add to the list of node to visits. So it's going to restart another loop, pop a new node, which is going to be the minimum because we are using a binary heap. So binary heap will always give you the minimum. And this way we keep going, visiting the minimum path node by node until we find this one. Makes sense?
Yeah.
Cool. Neighbors, I think we can ignore. Now, this one, part one, becomes as easy as create a cave map of 100, parse it, and find the shortest path to bottom right. This will return literally our solution. We return that, and that's it. Part two, and this is where I was stupid, and I literally said, okay, allocate 500, parse the input. The input is still 100 by 100, so in reality, we have a section of the grid that is really filled in with values, and all the space around it that is like zeros. And then when we call expand map with tile size 100, it literally takes 100 by 100 and copy everything around it in all directions. So this is super ugly, and maybe we should fix it.
And can't you you could have inferred that 100 from the constant in the type.
Yeah, I think we could make this cave map a little bit smarter, like a virtual array.
Yeah, but if you're using an array, you want the constant in the type to use the arrays and not vectors.
Yes, because if you use vectors, I mean, you could use vectors, nothing wrong with that, but you are allocating a lot more. With an array, you have
in theory is faster.
A chunk of yeah, exactly. And we can run the tests if you're curious, but I am quite sure that this was working last time I checked. Yeah, part two is not super fast, to be honest. Actually, we should maybe benchmark, and then we can try to see if it makes sense to optimize.
But I don't think the parsing is the problem. I don't think that filling the cave is the problem. I think the problem is just the graph itself. I mean, part one to me is running in Python in less than a second. Part two is running in 15, 14 seconds because it's 500 by 500. It means that there are 250,000 nodes to keep track of. Is a lot of data.
That's true, yeah. But we are not allocating all these edges eagerly. We only allocate them when we find them, I think. So we still rely on that grid as a way to build the graph as needed.
A quick mention. Ramsko was asking in the chat if there will be a repo for this. I sent a link to the PR. We usually merge the PRs just after the stream is over. Either sometime within the next few hours, depends on how busy we are, to be honest. So yeah, feel free to either branch off that or branch off main once it's merged. If you have ideas or suggestions, they'd be super welcome, by the way. So thanks for that.
Instead, the Python code is not there at all.
But yeah,
we could add it there, to be honest. Those are Jupyter notebooks, so
even if we add the links, right? If we make them public,
Or we can download them and commit them to the GitHub repository. Those are text file in the end. It's nothing fancy. I don't know if GitHub can preview Jupyter notebooks. No idea. But there are a lot of service that does that. So
I think you can preview some Jupyter notebooks in GitHub. I don't think you can run them, but if the output is already in the cell, I think it will be displayed.
We can
try. We can try, yeah.
Anyway,
it's actually pretty smart because, we'll see. Check one in and see what it does, right?
Yeah. So we have about 3 milliseconds for part 1 and 110 milliseconds for part 2. So it grows quite a lot in time from part 1 to part 2, like 30 times, right? More?
Yeah, 30, 35, 30 something. Obviously, Python is way slower. Also, using NumPy that is available in Colab could speed this up a lot. I wanted to do this in pure Python because I'm a masochist, probably.
Or you don't like NumPy. Tell us the truth.
I always have to Google so syntaxes. That can be true, to be honest.
Okay, so I don't know if we have a lot of time to try to do the optimization maybe and see if it's faster. We can try to do it in 5 minutes, and if it works, it works.
Do we see any kind do you mean the parsing stuff with the access method to map and update?
Yeah, I'm not really sure how to do this yet, to be honest.
Do you ever get cost? Where do you get the cost?
We get the cost when we do the parsing.
Yeah, but through access directly to the cost or with a method?
Let me show you the parsing, right? Where is it, the parsing? Here at the top, from string. So this cave here can be as big as you say with n. Hopefully you say a value that is bigger than the actual size of the input, because otherwise it's just gonna panic. But if you say here like 10,000 is n, it's just gonna allocate a grid 10,000 by 10,000, and then it's just still gonna fill a number for 100 by 100. Then when we call expand, you are copying those 100 by 100 over to the adjacent space.
And you don't want to copy anymore, but you want to keep the original one and compute every time the mapped value. But at that point, you are computing at every access. I don't know if probably this way is faster, to be honest. It's using more memory, but it's faster. Otherwise, every time you access a cell, you have to look at the modulo version of it, and then add check for the overflow, check for the overflow, and give back. So this can slow you down. I could try to do the same and see if Python is faster in that. Well, not now.
Could be interesting, yeah.
From the chat, Ramsco mentioned he's curious how we dealt with ownership and allocating, because it's not natural yet. I was going to say it's not very natural to us either, and although we've been doing it for a while now, we try to, or maybe does anybody want to answer what we can
try to use the last 5 minutes to just go in just chatting mode, so people feel free to ask us questions and we'll try to reply if it's generic about Rust like this.
Ownership at the beginning we were cloning like crazy, if you remember. Then we started to deal with references way more, also because the inputs are typically how do you say str references to str, so you can point to this big string that is your input, and sometimes a lot of exercises are about strings, so you don't have to parse really the string, you just have to take bits and pieces of it. Then when we have to parse, we had the biggest problem with ownership, I think, was when we were looping on top of something that we want to change. There was this a lot of exercise have this, so take this set, find the intersections between them and discard the one that are not in the intersection, and like this until you just have one out of it. And that between mutability, references, and ownership was a little bit crazy to follow. What do you say?
Yeah, we also had a lot of issues with mutable references and getting double references in some cases, if you remember that.
Yeah, especially when you start to use the iterator combinators like filter and map and all these things. Sometimes you get, reference, because those combinators are not trying to disrupt, or maybe the correct way of saying that is they're not trying to take ownership of your original iterator. So you get references into the previous data structure. And if that data structure already had references because you were mapping something else, you end up with references of references. And if you keep doing many like chaining of combinators, at some point we saw like 3 or 4 ampersands in the annotated type of the IDE. And that can be a little bit confusing sometimes.
Yeah.
But the good thing is that Rust most of the time manages to the reference on its own. So you don't need to say like asterisk, asterisk, asterisk. You just say from this object dot some method, and Rust is going to figure out, okay, you want to dereference all of them, and just call the method.
Yep. What's other thing? We had some fun with into iter as well, because I know some of them. But I don't remember what it was. It was early on where we had some issues with this. It wasn't references.
I think iter and into iter, one is borrowing and the other one is taking ownership. So when you're borrowing, you get references of the objects that the iterator is producing. When you are taking ownership, you get the actual object, but that means that after the loop, you cannot use that original structure anymore because you have consumed it basically with your iteration logic. So that was another pain point, because sometimes, more often than not in Advent of Code, you need to do an iteration, but that's just one step. Then you have to do something else. And if you have consumed all the data with the iterator, it's like, okay, now how do you access back to the original data?
And there we were cloning.
Yeah, sometimes we clone.
Even to zip the window. Now is when you want a tuple of value, the first one and the second one and the third one, the third one and the fourth one. There we were cloning to have 2 iterator and zip on top of them at the beginning. Now I think we are cloning, but we are cloning only the iterator, not cloning the original object. At the beginning, we were cloning all the objects.
Which was a little bit stupid, because we didn't realize that you can cheaply clone an iterator because it's just a view over a data set, right? So you are just cloning references. So that was much more convenient.
Yeah, references and a pointer.
Yeah, it's not allocation. Yeah. So.
Then another one that was quite interesting, that it was and this is something that comes up every time, and every time we are a little bit frustrated with. It's not easy to, if you are iterating over something using iterators, but you also want to mutate that data structure, it's not always easy to do, of course. The rules of Rust are preventing you from...
There is that nightly build function on top of set, what was discard, keep. There was a function on top of sets to...
Retain, I think.
Retain, right.
I was going to say...
on a
Go, Roberto, sorry.
That based on a logic, su a Boolean, you were able to filter the set in place and get back a reduced version of it. We tried to implement our own. Obviously, it was a mess because you were, like Luciano said, you have to alter something while you are looping on top of it. And the normal solution in Python is just to create another object filtering the previous one. But that is an allocation that in Python doesn't care, because Python is allocating a lot. But in Rust, it was feeling dirty to us to have to allocate an object when we already have the references. We have a nice set of references there, and we can just remove some lines and keep the allocation there.
So set retain, I think, was called. We can find the actual function somewhere and put it in the chat.
Yeah. Also, Ramsko said they usually try to have it work first and then optimize, and that's exactly how we operate as well. Working is better than perfect 10 out of 10 times.
Yeah, to be honest, we are also doing Advent of Code, so this is not going to be production code that is trying to make millions of requests or something like that. Hopefully, don't do that with our code. But yeah, it's just a nice excuse to get to see different use cases with Rust of things that we more or less know how to do with Python and JavaScript, because they are very dynamic languages. But then when you try to do them in a language with static types and compiled, and Rust also adds all these rules of the borrow checker, it becomes more interesting, and you need to think more about, okay, what's happening with the memory? Can I do this differently? And yeah, for us, it's just an exercise for now, but it's a nice way to learn Rust.
Yeah, I find it's cool that it gets you to think about how you write your code in a little bit of a different way.
Yeah, it was ages that I was not thinking of stack and heap. I mean,
yeah, well, when we do Python and we do JavaScript or whatever, you don't really have access to this stuff.
And also was funny to go to the bare metal with the Raspberry Pi Pico.
Oh yeah,
because you don't have the heap. You just have the stack. So no vector, no hash map. You have to implement your own once with fixed allocation, and everything is fixed allocation because it's a binary without an operating system. Guys, no operating system there. There are obviously libraries that mitigate that, and I think there is also some runtimes that are behaving like an operating system. I mean, there is a real-time OS, but there was something for Raspberry Pi Pico and Rust that is coming out.
Actually, this is the episode. If someone is curious, here in the chat, by the way, you can check out that YouTube for other episodes. But yeah, that's the link if you want to see our experiments with the Raspberry Pi Pico running Rust.
Yeah, that was interesting. Well, I found it interesting.
Yeah, especially because I don't know almost anything about microcontrollers and how you program them. So it was like a full-blown crash course by Roberto to us to understand how all this thing works without operative system, and you need to write everything from scratch.
Yep. It was cool.
Guys, when you work inside a browser, there is so much happening before arriving to a transistor.
Yeah, that's true. Now, do we have any more questions, or do we want to close it here?
I don't think we have another question. I think we can close, yes.
Yeah, let's wrap it up for today.
Alrighty. So, in saying that, well, Luciano already posted a link to a recording on YouTube. There will be a recording of this one as well on YouTube. You can find the link to the channel in the About section on Twitch. In case you're watching this on YouTube, we do live streaming every Monday at 6 p.m. Dublin time. So yeah, check out the link. Apologies, in the YouTube description. Give us a follow so you can be notified when we go live. Feel free to leave us comments or open PRs on the repo. I know I sent a link earlier to the PR that we're having now. So yeah, if you have a suggestion or contribution, feel free to branch off that and open up a PR. We'll take a look. We should probably put a banner with the repo just in case. Give me just a sec. Beep, beep. There we go. So there should be a banner playing now. That's where you can find the code. So yeah, everything's well accepted. We're trying to learn. So as you've seen, not everything that we do is perfect. Some things aren't idiomatic and so on. So let us know if you have any ideas or any thoughts. Thanks for all the suggestions and collaboration in the chat. It was absolutely great. And I think we're going to raid someone, right, Luciano?
Yes, but because I have to search for it, it's going to be a surprise. So stay tuned with us for other 15 seconds, and hopefully you are going to enjoy our raid.
We play some elevator music.
Yes. So see you next time. Thank you.
Bye.
Bye.